Assalamu alaikum students. So today we are going to derive an equation for head losses inside the pipes, and we have already derived one equation for head losses inside the pipes, but that was for a horizontal pipe and the flow was laminar. But in today's lecture, what we will do, we will derive an equation for head losses in pipe that will be applicable for both laminar and turbulent flows, and we will be doing that with the help of our energy equation and the momentum equation that we derived using the Reynolds transport theorem. So let's move on. So head loss, the overall head loss is equal to the major head loss and the minor head losses. So in this lecture we will be deriving an equation for the major head losses. And what are the major head losses? Major head losses are due to the viscous effects in the straight pipes. These are the losses that occur inside the pipes. You remember the pipe system, that the pipe system contains generally the pipes, different type of walls and different type of bends. So the losses that occur inside the straight pipes, they are called the major losses, and due to the viscous effects in the pipe components, they are called the minor losses. And by pipe components we means the walls, the nozzles and the bends that occur in a pipe system. And this does not mean, please don't be mistaken by the names, that this does not mean that the major loss will be always higher than the minor losses. It can also be the other way around, that the minor losses can be greater than the major losses. It varies from one condition to another. So please don't be mistaken by the names. They are just names to differentiate one loss from the other. And as again, the major losses are inside the straight pipes and the minor losses occur in the components that exist in a pipe system. So what we are going to do, we are going to derive an equation for the head losses that are in these straight pipes, the major head losses. And for that, what we will do, we will take this scenario where we will take a pipe section. It will have point 1 and point 2, and it will have point 1 have an elevation of z1, z2 from this datum, and it will also have a characteristic length of delta L. So we will apply our energy equation and our momentum equation on this scenario, and we will try to derive our head losses, our major head losses. So this is what our energy equation is. We already discussed that in our previous lecture as well. So here we will assume that our flow is steady, the flow is fully developed. So when a flow is fully developed, then the velocity will be a constant. Means that point 1 and point 2, the velocity will be the same, and alpha 1 and alpha 2 will also be the same. So these two components will cancel out. The velocity will cancel out due to our steady state assumption. Then we will simplify this equation and will write it in terms of the head loss. And this is how, after cancelling these velocity terms, this is how this equation will look like. And after further simplification, we will get an equation of head loss, that is delta z plus delta p over, and we can also write this specific weight in terms of rho g, that is density into gravitation acceleration. So so far this is our equation for the head loss. We will remain it as such. We will come back to this equation a bit later after using our momentum equation and applying it on this scenario. So let's do that, and then we will later switch this term inside the momentum equation to get our term for our major head losses. So let's do that. Now we will use our momentum equation, and by using our control volume and control system analysis, we will use the same scenario that we used for our energy equation, and we will actually apply this momentum equation on this scenario. We have a section 1, that is the inlet, section 2, that is the outlet, then we have the axis of this pipe, and then as you can see, we will be summing up the forces. So we will also take the weight of the water into the account, because this is not a horizontal pipe, and it will comes out to be something like this, something like this, and this is W and this is theta, and this term right here will be, this side will be W sine 30 sine theta, sorry, and we will write this W in terms of specific weight. So this will come out to be W specific weight, as you can know, is weight per unit volume. So W is equal to specific weight into volume, and specific weight into volume. So for volume we will multiply the area with the length, so we will get a specific weight, that is gamma into pi r square delta L. So what we will get for W sine theta, we will get a gamma pi r square delta L sine theta. So this will be for W sine theta, and this is the component that is going to be added when we take the summation of forces. There will be a pressure force at point 1 and for point 1 should be greater than point 2, so that the flow can move in this direction. There should be a pressure difference. Point 1 should have a higher pressure than point 2, so we can write delta P as P1 minus P2, and P1 can be represented as delta P plus P2. And similarly we are talking about summation of forces, so we will write pressure in terms of forces, so we will also multiply that with the area. So pressure is equal to force into area, so that will be pi r square. Similarly there will be pressure at P2, and P2 will also be P2 into pi r square. Will be also the pressure force, sorry, it is the force terms right here. So at F1 and F2, this will be P2 into pi r square. So this is the forces at section 1, at section 2, and then these are the component of weight that is going to act in this direction. So these are the forces that we are going to add up, and then there are two control surfaces. There is control surface 1 and control surface 2. So we will take the velocity at control surface 1 and control surface 2, so this will be our velocity, and then these terms, this rho v into a, this will come out to be m dot. M dot is our mass flow rate, and that is equal to rho v dA. So that will come out to be our m dot. So we will write this for the control surfaces, and this will be negative for section 1 because it is the fluid that is going in, and it will be positive for section 2 because that is the fluid going out. As you remember, we already did that when we solved the momentum problems, and for control surfaces we already had that assumption sorted out. So the control volume term will be 0 because we have already stated that our flow is steady, it is not changing. So with respect to time there will be no change inside the control volume, so that term will come out to be 0. So these are the assumptions, and these are the forces that we are going to take, and then we are going to write an equation which will be solved for our shear forces. So let's do that. Let's write that equation. On the left hand side we will take this and write the equations on the left hand side. These will be the summation of all forces at section 1, that is P2 plus delta P minus P2 pi r square plus rho g pi r square delta L sin theta. This is the weight term that we already saw. You can also write gamma in terms of rho g, you already know that. So then will come the shear force, the shear forces that are also acting on the wall. So that they will be minus tau W into the area 2 pi r delta L. So these are the forces that we added. These are the summation of the forces. Then on the right hand side we will write the control surface term. So is equal to, I will write it here. This is the left hand side. This is the right hand side. On the right hand side, we will write the force, the control surface terms, and they will come out to be V1. V1 will be minus rho V1 A1 plus V2 rho V2 A2. And we can also write this as m dot V2 minus V1. And as you already know, we already said that our velocity is the same. So velocity at section 1 is same, and velocity at section 2 is also same. So this term right here, this term, the control surfaces terms, will also come out to be 0. So what we will be left with, we will be left with the summation of forces, and the control surfaces terms will be equated to 0, because we already assumed that this is a steady state, velocity is not changing. So at the control surface 1 and control surface 2, the velocities are the same. So the right hand side of this equation will come out to be 0. We will only be left with the pressure forces acting on section 1 and section 2, the weight of the liquid, and the shear forces that are acting on the sides of this pipe. So now we will work with this equation and we will simplify it a bit more. Here we can also draw another triangle if we like to. We can also draw another triangle to take delta z. Delta z will be the difference between z1 and z2. So delta z will be z1 minus z2. And if you can draw delta z here, so delta z will be this length right here. So delta z can be also drawn in terms of a triangle. If we take this length as delta z, this will be delta L, and we can actually make a triangle as theta. So by taking sine theta will be equal to delta z over delta L, and delta z will be equal to delta L sine theta. So we will take this term delta z, and we will substitute this delta L sine theta with delta z wherever we see this term. So now let's do that and simplify this term also, and we will get a simplified term, that is delta P pi r square plus rho g pi r square delta z minus shear stress 2 pi r delta L is equal to 0. Just rub that off. So now this is our equation. What we will do to simplify it a bit more, we will divide this equation by, we'll divide this equation by rho g pi r square. So by dividing this by rho g pi r square, what we will get, we will actually get this, that delta z plus delta p over rho g, and taking this term on the right hand side, we will get 2 dot w over rho g delta L over r. So as you can see, we should write this a little bit finer. This is delta p over rho g. So as you can see, this term right here, we had a relation for this term, and this was equal to the head loss. As you remember from the energy equation, this term was equal to the head loss that we did in the previous slide. So we can also equate this to the head loss. So this is our another equation for our head loss, and this equation came up by comparing the energy and the momentum equation. So this is our another equation for our head loss, and now what we will do, we will actually find our shear stress, and by using the dimensional analysis method we will actually take a certain value of a shear stress by using dimensional analysis method. So now let's do that. And to do that, we will say that our shear stress, that is tau W, is a function of density, velocity, viscosity, that is the diameter of the pipe, and epsilon. Epsilon is the absolute roughness of the pipe. Absolute roughness of pipe. So this is the absolute roughness of the pipe, because the roughness of the pipe also causes some shear stress, and it will also be responsible for head losses. We will see that in a bit, in a while. And to solve this with the help of dimensional analysis, we will get this term, that is 8 tau W over rho V square is equal to, that is F, this is the friction factor, and this is also equal to, this is also the function of Reynolds number and the roughness of the pipe. So this is also called the Darcy friction factor. This is also called Darcy friction factor. So these are the terms that came out from the dimensional analysis, and this is the absolute roughness of the pipe, and this is actually this absolute roughness is of the pipe, but of the internal surfaces. We are talking about the internal surfaces of the pipe. So now we have another term for our shear stress, so let's simplify it a bit more and write it in terms of this, that tau W is equal to rho the Darcy friction factor V square divided by 8. So we had another term for our shear stress, the wall shear stress, that we got from comparing the energy and the momentum equation, and that term was tau W is equal to rho G, that is RHF over 2 delta L. So by comparing these two equations, we will get another term. So let's compare these two, that is rho G R HF over 2 delta L is equal to rho Darcy friction factor V square over 8. So by comparing these two equations and simplifying it a bit more, let's give some space right here. Let's give some space, and after comparing these two equations, let's write them here. We will get our head loss. Our head loss due to our major head loss as rho F V square 2 delta L divided by 8 rho G R. So after cancelling some terms, what we will get, our major head loss HF will be equal to the Darcy friction factor L over D and V square over 2G. This equation has a specific name, and this equation can be used both for our laminar and turbulent flow, and this equation will be used for finding the major losses in the pipes, and this is also called the Darcy-Weisbach equation. Darcy-Weisbach equation. So this is for the major losses inside the pipes, inside the straight pipes that we have in our pipe system. And as we discussed earlier, this equation is derived with the help of the energy and momentum equation, where we got two terms for our head losses, and then we used our dimensional analysis method to actually come up with the term for our shear stress, the wall shear stress. And we there were introduced with the help of a Darcy friction factor, which is a function of Reynolds number and the relative roughness of the pipe. And then we compared the shear stress value that we had from our dimensional analysis and the shear stress value that we had from our momentum and energy equation, and then we compared them so that we can get our term for our head losses. These are the major head losses, as we already discussed. These are our major head losses. These are our major head losses. So this is an equation for the major head loss inside the pipes, and they can be used again for both laminar and turbulent flow, and they are also called the Darcy-Weisbach equation. So now, after deriving the equation for the head losses, the major head losses, what we had that the major head losses are equal to the friction factor, the L by D ratio, and the V square over 2G term. So now what we are concerned about is the friction factor. And as we saw in the dimensional analysis that we did in the previous slide for the wall shear stress, we saw that the friction factor is a function of Reynolds number, and it is also the function of relative roughness of the pipe. So now what we are concerned about, the friction factor, that what will be the friction factor for laminar flows, what will be the friction factor for transitional flows, what will be the friction factor for fully turbulent flows. So now let's see that how we are going to find the friction factor for laminar flows. And for laminar flows we will be using this equation that we already know what this is. This is the equation for Newtonian fluids, and this is the neutral law of viscosity, that shear stress is directly proportional to the strain rate. What we will do, we will put here the velocity equation that we derive for the parabolic velocity profile for laminar flows, and we know that that equation is equal to like this, that is the center line velocity 1 minus r square divided by the characteristic radius of the pipe. So this is the equation for our laminar velocity flow profile. What we will do, we will put this equation right here, and then we will take the derivative with respect to r. So that's how this equation will look like once we put it here, and then after taking the derivative we will get this equation, and then it will further simplify into this. So this is what we get, that is the viscosity, the average velocity, the radius, and 2r. So if we take at the wall that the radius is maximum and we put r is equal to d by 2, so we can actually get our value for wall shear stress, that is 8 mu V average over d. Further, we know that from dimensional analysis we had this formula that our friction factor is equal to 8 times the wall shear stress divided by the rho and V square average, the average velocity. So now what we will do, we will put the value of the wall shear stress in this equation. So we will get a friction factor for our laminar flows, and we will use that equation to calculate the friction factor for our laminar flows whenever we are talking about laminar flows, and when we are concerned about finding the major losses inside the laminar flows inside the straight pipes. So after putting the value of the wall shear stress, this is how this equation will look like, and after simplifying it a bit further, we will get our friction factor for laminar flow as F is equal to 64 over Reynolds number. As you can see this term right here, this is rho Vd over and mu is in the numerator, so this is equal to 1 over Re. This is equal to 1 over Reynolds number, so that's why this terms comes out to be like this. So this is our friction factor for our fully developed laminar flow. So whenever we are going to use this equation for major losses inside a straight pipe and the flow is laminar, so we will use a friction factor. We will actually calculate the friction factor using this equation, and this will help us in finding our major head losses. So now let's have a look at the other flow regimes, that is the transition flow regime and the fully turbulent flow regimes. And obviously this will accurately calculate the friction factor for a known number that is less than 2000, and we know that this is the laminar flow regime. So now for the friction factor for transition flows, we know that there is no accurate method to actually determine the friction factor for transition flows. We will be more concerned about finding the friction factor for our turbulent flows, and they must account for the eddies, and how these eddies occur we look into it in a while. But there is no theoretical method for determining the friction factor. As you can see, we derived a friction factor for our laminar flows, and we used a theoretical method for that. But for turbulent flows, there is no actual theoretical method. We will rely heavily on experimental and empirical formulas. So as you know, this is the velocity profile for our turbulent flow, and there is a viscous sublayer, a laminar layer near the wall of the pipe. So this is represented as delta W, and the eddies are actually generated in this region right here, and it depends on the roughness of the pipe, because we know that the friction factor is a function of Reynolds number and the relative roughness of the pipe, the epsilon over d, that is the relative roughness term. So the absolute roughness is the distance that imperfection protrudes into the flow. So what does that mean? This means that how much the pipe is rough. If the pipe is rough enough that it protrudes into this length, so it will ultimately result in the eddies. As you can see in this diagram, that if that epsilon is almost equal to this length, then it will protrude, this layer will be disturbed, this viscous sublayer will be disturbed, and it will actually result in eddies, and it will actually disturb the flow. So in turbulent flows, rough walls can induce eddies outside the viscous wall layer, increasing the major head losses. So the roughness of the pipe actually results in increasing the major head losses inside the pipes, as we already discussed that the major head losses are concerned about the losses inside the straight pipes, and the minor losses are the losses that are concerned with the losses inside the components of the piping system. So actually the main factor inside the pipes is the roughness of the wall. So here, as you can see, the eddies actually disturbs the viscous sublayer, and they also result in increased major head loss. And as you can see, this can be said that if for concrete pipes, you can say that there will be a lot of eddies, because concrete pipes are not that smooth. So if you take plastic pipes or steel pipes, they are actually smooth as compared to the concrete pipes. So for concrete pipes, you can say that there will be actual eddies, and they will result more in the head losses. But in case of plastic pipes and steel pipes, there will be less head losses due to the wall friction or due to the wall roughness, because the wall tip actually looks smooth, but if we take the microscopic view, as you can see right here, the wall is actually rough, and it results in eddies. It actually disturbs this viscous sublayer that induces increased major head losses. So hydraulically smooth walls, what does that mean? That the absolute roughness, that is the epsilon, is equal to 0. There is no such thing as hydraulically completely smooth walls, but if the epsilon is very less, means that the roughness of the pipe is so much that it is not disturbing this viscous sublayer. So we will term that it is the hydraulically smooth wall. But if the roughness is so much that the epsilon term is almost equal to the viscous sublayer length, then we will say that it is the hydraulically rough pipe. But if the epsilon is almost zero, then it will not disturb this viscous sublayer region, and it will result in less major losses inside straight pipes and will reduce the eddy formation. So now let's see that how will we find the friction factor inside the turbulent flows, and for that we rely heavily on the experimental data. So Colebrook in 1939 derived this equation with the help of experiments, and this equation can be used to actually calculate the friction factor. But as you can see, this is a very complex equation because there is F on both sides, so you will have to do a lot of iterations, or you need a computer to do that iterations for you. So it will result in a lot of time wastage. So the value of F is determined by using computer program or an iterative scheme. So what they did, actually Moody came up with a chart that in 1944, and by using that chart we can actually graphically represent the Colebrook equation, and by using that chart we can actually find our values for our friction, our Darcy friction factor for Reynolds numbers that is greater than 4000. So Moody helped us by graphically representing this equation on a chart, and what we will do, we will actually read that chart and we will take the value of our friction factor for regimes that are lie in the turbulent regime, that is for Reynolds number greater than 4000. There is also another equation, that is the Haaland formula. The Haaland formula in 1983 also calculated the friction factor by using this equation, and now you can see that you actually need the value of relative roughness and Reynolds number to use this equation and find the friction factor, and the this equation will result in a value that will be that will lie within 2% of the result that we get from the Colebrook equation. So this equation was derived later in 1983, but until 1983 we were relying heavily on Moody's chart to find the friction factor for pipes in the turbulent regime. So now let's have a look at the Moody's chart and see that how it helps us by finding the value of friction factor for turbulent regimes. So this is the Moody's chart, and as you can see that the values that this chart was plotted by using the Colebrook equation, and this is the value of, there is the value of friction factor here on this side, and the horizontal there is the Reynolds number, and here it is the relative roughness epsilon over d of the pipe. So if you know your Reynolds number, if say your Reynolds number is 5000, that your RE is approximately equal to 5000, so it will lie in this regime, it will lie in this regime right here, it will, this is the 5000 regime Reynolds number, and let's say that your relative roughness is somewhat 0.04, that your relative roughness is given as 0.04. So as we already know that how that we read charts, we will draw a line perpendicular here, and then we will draw one horizontal line here, and where these two lines intersects, so from there we will actually see our friction factor. So for that our friction factor will come out to be somewhat 0.2678. so if we use these values, our friction factor will come out to be 0.028. so this is the Moody's chart, and this chart helps us to actually find the friction factor. And you can also see that there are also laminar regimes, the transition regime on this chart, so we can actually use this chart also to find our friction factor, our Darcy friction factor for a laminar regime also, but we have a formula for laminar flow regime that is much easy, that is F is equal to 64 or Reynolds number. And for transition flow, we can use this chart. For wholly turbulent flow, we can use this chart, and what we need to know, we just need to know our Reynolds number and our relative roughness of the pipe, and that these two values can be used to actually find the friction factor. And as you remember, as I mentioned earlier, this chart was plotted by using the Colebrook's equation. And as you know that in 1939, computers were not readily available, so people had to rely heavily on the iterative scheme, their mathematics, their numerical iterations to actually solve that equation. But Moody helped us, and he actually plotted the equation on a chart. So this is how the Colebrook equation on a chart looks like. And with the help of that, we can actually now see different friction factors. We can find different friction factors for our turbulent flow regime.